Welcome back. We've now talked individually about three major orbital regions around Earth: low Earth, medium Earth, and geosynchronous orbits. To help summarize what we've covered so far, I want to compare these regions, focusing in on just a few things. First, we'll look at the number of satellites currently operating in each region. Basically do like a census of where satellites live in orbit. And as a question on that census, we'll also ask what the satellites actually do in these regions. Second, we'll consider satellites whose job is to take pictures of the Earth and ask, where is the best place to orbit to get good images? We'll third focus on satellites whose goal is communication. So where is the best place to orbit if you want to broadcast TV signals or provide broadband internet? And then finally, we'll discuss different requirements for different orbital regions for what happens when a satellite reaches the end of its usable lifetime. Okay, so first let's get a sense for the number of satellites across our three orbital regions. The total number of satellites is increasing literally daily. For us today, there are nearly 9,000 active satellites in orbit around the Earth. But between checking the exact number a couple days ago and this morning, 41 new satellites had been launched. So if you want to know the exact number right now, there are several websites you can go and get this number in a single click. And we'll list one here and post the link again in the supplemental materials. So although the total number of satellites is changing, what isn't changing is the relative number of satellites in each region. So in the last few years, 90% of all active satellites in orbit in low Earth orbit, in LEO. And this partly reflects the fact that LEO is closest and easiest to get to, but there are other considerations that we'll discuss that are driving the majority of satellites to this region. Medium Earth is a pretty lonely place due to its extra nasty radiation environment, and as a result, merely 3% of all active satellites orbit in MEO. But those 3% are super important, as most of these medium Earth satellites are GPS or other navigation system satellites. And then finally, the remaining 7% of satellites are in geosynchronous orbits. But unlike LEO and MEO, where satellites occupy orbits with a variety of orbital periods and inclinations and phases, geosynchronous orbits share a single orbital period, and geostationary satellites share the same orbital inclination. So this 7% of satellites is packed into like a super crowded bracelet of satellites orbiting around the Earth. So that gives a sense for where satellites orbit, but let's also break down the satellite population into what they actually do. Satellites perform different functions depending on their payloads, that is like the stuff that they're carrying. And the three most common functions for satellites in orbiting Earth are communication, imaging, and navigation. So 60 to 70% of satellites are for communication, so that's TV signals or internet providers. 20% are Earth observations, so these are satellites that take images of Earth. And again, 3% are navigation. And you'll note that doesn't quite add up to 100%, and the rest are things like technology development or satellites that take images in the direction away from Earth. We'll focus an entire module on satellite payloads and discuss these functions in more detail soon. But for now, we'll think about the two most popular satellite functions in terms of orbital region. So first, the 20% of satellites that are Earth observation. Mostly these are satellites whose purpose is to take pictures of Earth. So think weather satellites or Google Earth images or even spy satellites. The cameras on these satellites are not all that different from the camera that's in your phone. And a camera has a certain field of view that is the size of the image. So if you're trying to take a group photo and there are people who need to squeeze in on the edges to try and get into that field of view, that's what we're talking about. Cameras also have a certain resolution, that is how fine detail they can make out. So when you're taking a photo of something super far away, you want higher resolution to make out the object in the distance. By far, what determines the field of view and resolution of a camera on a satellite is where it is in orbit. Closer to the Earth, we get smaller field of view, we see less of the Earth, but the images have higher resolution. Further from Earth, we can see more of the Earth at one time, but at much lower resolution. So for example, a typical satellite in low Earth orbit can see a region that's roughly 100 kilometers or miles across and can make out details on the scale of a meter or a few feet. that same camera in geosynchronous orbit can see the entire Earth, or at least the half that's like facing it, but at much lower resolution, making out details on the scale of like 1 kilometer or 1 mile. Depending on your goal, you'll make different choices. So if you want to monitor, say, large-scale weather patterns, placing a satellite at geostationary orbit makes sense, where you can get continuous imaging of the whole Earth. But if your goal is to monitor for coastal flooding, you need sharper images provided by placing your satellite in low Earth orbit, but at the cost of getting images of any one region less often. We'll come back to how imaging cameras themselves work later on, but answering our original question, where is the best orbital region for satellites that take pictures, the answer really depends on your goals. Moving to our next topic, the majority of active satellites, 60 or 70%, are involved with communication. So that's broadcasting TV signals or cell phone or internet. What is communication? So for a satellite to communicate with Earth, it usually does so using radio waves. So that's the same thing as the wireless internet you might be using to watch this video. Both satellites and your wireless router are communicating using radio waves at different frequencies to transmit information. Radio waves are a form of light, and we know that light travels at a finite speed. It's fast, 300,000 kilometers a second, but it still takes time to get places. So in 1 second, light can orbit around the Earth's surface 7.5 times. Okay, that's pretty fast. On the other hand, if you want to communicate with the moon, it takes light over 1 second to make that round trip. Geosynchronous orbits are not as far as the moon, but it still takes noticeable time for light to travel there. The round trip is about 1/4 of a second, so enough to be annoying during a phone call. This time lag is called latency. And for some applications like cell phone or internet providers, you want very low latency, very little lag time. For broadcasting a TV show, you can tolerate some latency. Geosynchronous orbits have some latency, but with a single satellite, you can reach a large region on Earth. So this has been the choice for satellite TV providers, some latency, but wide coverage with a small number of satellites. On the other hand, if you want to provide broadband internet, low Earth orbits are attractive because of that low latency. And the problem until recently has been that a single or even a few satellites placed in low Earth orbit can't provide full coverage to a given region. This has motivated satellite constellations with hundreds or even thousands of satellites in low Earth orbit. So for broadband internet providers, the choice has been low latency and thousands of satellites. And while we're on the topic of latency, for the case of GPS or other navigation satellites, latency is actually a good thing. We actually need it for GPS to work. So GPS satellites are intentionally placed out in medium Earth orbits so that there is enough latency to measure the light travel times between us and those GPS satellites. We turn those travel times into distances and triangulate our position. So latency is a good thing for GPS satellites. Okay, our final point of comparison for our 3 orbital regions is what happens when a satellite reaches the end of its mission. Satellites are designed to have a finite lifetime. The limiting factor is usually the amount of onboard rocket fuel needed to do small course corrections or avoid collisions, but other limiting factors could be onboard battery life or the amount of coolants to keep sensitive cameras working. The end-of-life recommendations depend on orbital region. For medium Earth satellites, there's no recommendation. This region is so sparse that satellites basically continue on the same orbit forever, even when they stop working and nobody cares. This is different in LEO and GEO, where things are far more crowded. In both regions, there are strongly worded suggestions and vaguely enforced regulations. For LEO, a satellite that is no longer in operation should be deorbited, that is pushed into lower orbits where it burns up into the Earth's atmosphere, within 5 years of the satellite's end of mission. And 5 years might seem like a long time, but until just last year, the suggested time limit was 25 years after end of mission. You might ask, how is this enforced? And the answer may be surprising and is something that we'll actually explore a little bit later. In low Earth orbit, the FCC, so that's the U.S. Federal Communication Commission, is setting these guidelines. And in order to get an FCC license to communicate with your satellite, you must show that you'll have enough fuel to dispose of your spacecraft as soon as practical and no more than 5 years after end of mission. In geosynchronous, it's the ITU, the International Telecommunication Union, that regulates geosynchronous orbital slots, and they also have end-of-life recommendations. As we mentioned last segment, the geostationary or geosynchronous satellites are far from Earth. So rather than returning to Earth at the end of mission, geosatellites are nudged into a more distant graveyard orbit at the end of their usable lifetime. So, coming back to our question, where is the best place to put a satellite? The answer really just depends on your goals. Operating in low Earth orbit allows you for higher resolution, sharper images, more timely communication, low latency. However, LEO satellites zoom overhead, and that's okay for some applications, but if you want continuous coverage in any given region, you need multiple satellites to accomplish most goals in LEO. In contrast, geosynchronous orbits provide continuous access to large regions on Earth and wide field images. The flip side is high latency, communication time lags, and those images don't have particularly good resolution. So given that 90% of all active satellites are in low Earth orbit, this gives you a sense for how these choices often play out. One factor we haven't mentioned yet is cost. So getting to low Earth orbits are just easier and cheaper compared to medium Earth or GEO orbits. And in fact, satellites going to GEO or MEO are typically launched into low Earth, they rest for a moment, and then are transferred out to more distant orbits. In the next segment, we'll actually think about how to get into orbit, as well as how to move between orbits once we're there.